All right, so let's just begin this. So this is our very first content review video for Unit 4, Chemical Reactions. And this is, well, I reused the slide a lot for Science Olympiad and for last year when I did this unit, and hopefully it helps you guys a lot. And I already posted the slides, but maybe the voiceover might be helpful as well. And tomorrow I'll be going over more challenging practice problems. So let's just start with the very basic chemical reactions. So we have four main types of reactions. The first one being synthesis, which we see over there is just one compound plus another compound gives us another compound. So an example will be H plus Cl coming together to form HCl, hydrochloric acid, synthesis. Decomposition is just the inverse or the opposite of synthesis, where you have, say, for example, HCl, hydrochloric acid, and that just breaks off into H plus and Cl negative. It's just the opposite of synthesis. Single replacement is where you have a compound AB and a separate compound or separate element, I should really say, of C, and the B and the C separate, or they swap places. And that's what you call single replacement. Double replacement is essentially the same thing, relatively easy to follow. You have AB and CD, and they just kind of swap partners. Um, it's kind of like going on a double date, and then you kind of swap partners midway is essentially what's going on here. So those are the main four types of chemical reactions that we kind of classify. Another one is, was it combustion, which is essentially where you have a hydrocarbon reacting with oxygen, and the products will always be water, H2O, and carbon dioxide. Those will always be your products, and I did not list that here, but you should have covered combustion in the last unit, I think. And there's also, along with the different types of reactions, there's different types of ways you can represent these chemical reactions. So the most familiar, which is coming from stoichiometry, is known as a molecular equation, which is the complete balance equation to represent all the reactants and products in a chemical reaction. So the example I have here is lead nitrate reacting with lead iodide, which gives us a solid lead iodide and sodium nitrate. So then that's the way you might be familiar with the molecular equation from stoichiometry. However, another way you could represent this is through the complete ionic equation. And the reason why we can do this is because if you notice over here, it says lead nitrate AQ. AQ essentially means it's aqueous, which means it's dissolved within solution. So if you were to really look at this from a physical point of view, that PbNO3 is not really found as PbNO3 it's actually found as individual lead ions and individual nitrate ions because they're dissolved within solution. So then we can essentially break off all of these salts into their aqueous counterparts. So lead nitrate goes into lead and nitrate. Lead iodide goes into, sorry, not lead, sodium iodide goes into sodium and iodide. And sodium nitrate goes into sodium and nitrate. The only exception here is the lead iodide. And the reason why we do not count the lead iodide is because if you notice over here, the state of matter is S, which means solid. And that essentially means that that will be our precipitate, which means within solution, lead iodide does not dissolve. So therefore, if you're to look at it from a physical point of view, you will find lead iodide as solid lead iodide. And the reason why we want to do this complete ionic equation is because you might notice that we have 2 moles of nitrate on both sides and 2 moles of sodium on both sides. So what we can do is that we can actually cancel those out. So we can cancel out the nitrate, we can cancel out the sodium, and therefore we just get the lead and the iodine in the lead iodide. And this is called the net ionic equation, which it only includes the species involved with this unique chemical reaction, this chemical reaction being precipitation. It does not include the spectator ions. The spectator ions are anything that got canceled out. So in this case, the nitrate, which were canceled out because we have two on both sides, and the sodium, which we have two on both sides. Those were canceled out, and since they were canceled out, they're called spectator ions. Then here's some practice problems, but the answer key are kind of right below. So yeah, sodium fluoride. Yeah. All right, so then the very next topic is solubility. Sorry. And there's different representations of solubility. Or sorry, there is only one representation. This is a representation of solubility, specifically of a salt crystal. So we can call this NaCl within water. And what you might notice is that, or if you're to put salt into water, you'll notice that it dissolved into water. Why does that happen? Well, the reason why that happens is that the water molecules essentially tear apart the ions apart. And because of that, we can see that there's a certain orientation that they have. So, for example, when it comes to water, the hydrogens are more positive than the oxygen because of the polar bonds, in that you're going to have a lot more negative electrons over the oxygen. So then because of that, that makes the hydrogen areas a lot more positive, which makes sense that the hydrogen areas kind of surround the negative anion. So for example, that could be the chlorine. When it comes to the cation, so for example, Na, sodium, due to the polar nature of water in that the oxygen is a lot more negative, the negative oxygen surrounds the positive cation. So then we can kind of see how these different salts are kind of broken apart by the water molecules. And these water molecules take certain arrangements or certain orientations around these water molecules due to the charge of the ions and the polar nature of water. So make sure to pay attention to the charges. All right. And then the very next topic is the introduction to acid-base reactions. Um, so when it comes to one definition of the acid-base definition, we're going to focus on the Bronsted-Lowry definitions. So for example, in this case over here, a Bronsted-Lowry acid is any substance that kind of donates an H plus ion, while a Bronsted-Lowry base is anything that accepts an H plus. And it's important to note that water can act as both a proton donor and a proton acceptor, and that's why we call it amphiprotic. Um, and then another term that you should be familiar with is the conjugate acid and the conjugate base. So the conjugate acid is the substance that forms after a base gains a proton. So it's essentially because when you have an acid-base reaction, if you're starting off with an acid, that's going to turn into the base or going to turn into a base. But to kind of differentiate it from, oh, you start off with a base, end off with an acid, we just say, oh, conjugate base. Essentially saying that, oh, at the end of the reaction, we're going to have a base. So we're going to call that the conjugate base. Then the conjugate is just indicating that, oh, it's a product. Same thing with the conjugate base. If one of your reactants is an acid, that acid will turn into a base. But then since that's a product, we'll just call it a conjugate base, indicating that it's a product, but it's also a base. So then we have a conjugate acid base pair over here. So you might see CH3COOH, which is acetic acid. That will be the weak acid. And sorry. And we know that this acetic acid is a Bronsted-Lowry acid in that it gives up an H plus because we see a CH3COO negative. And we know that that is a base because it can accept an H plus to turn into the acetic acid before. However, since it's a product, we're going to call that the conjugate base because it's on the product side, but it's also a base. Sorry. And then when it comes to some acids, not all acids and bases are equal. So some acids are significantly stronger than others. So the seven strong acids are, like us, or on the slide, HCl, HBr, HI, HNO3, H2SO4, HClO4, and HClO3. And the good thing, specifically with AP Chem, is that anytime you see an acid and it's any one of those seven, then it's automatically a strong acid. And anytime you see an acid and it is not any of those seven, it's an automatic weak acid. And then for the bases, the strong bases are essentially the group 1 and group 2 metals minus Mg and Li, because MgOH2 and LiOH are solid. So they do not really precipitate or they do not really dissolve. So the good thing here is that anytime you see any of those strong bases, it's going to automatically be a strong base. Anytime you see a base or you're given a compound and you're told that it's a base and it's not any of those seven, it's an automatic weak base. Now you might be wondering, well, what's the difference between a strong acid and a weak acid? Well, a strong acid is anything that completely disassociates. So for example, if you have a certain amount of HCl, that HCl will completely break off into all H's and all Cl's. However, going back to the last slide, sorry, you might notice that the acetic acid might say weak acid. So what that essentially means is that you might have a certain amount of acetic acid. However, not everything will dissociate. So for the final, I guess like after the final reaction, you're going to have some strong acid. You're going to have some acetate, which is the CH3COO negative. However, you're also going to have some CH3COOH left that did not react. So therefore, we call that a weak acid and that it does not completely break off. While the strong acid and bases, they do completely break off. And another thing we should note is that, or another thing we should talk about are called neutralization reactions. So when it comes to neutralization reactions, if you have a strong acid and a strong base, the result will always be water and a neutral salt. The neutral salt meaning you're going to end off with a pH of 7. So for example, if I combine HCl and NaOH, oh sorry, LiOH is a strong base. I think I previously said LiOH is not a strong base. It is a strong base. I don't know why I said it's not. But anyways, back to this example. If I have HCl and NaOH, the reactant will end up being OH and H coming together to form water, and Cl and Na coming together to form NaCl. So you might think to yourself, is this a double replacement reaction in that we're kind of swapping partners around? And you're right, it is a double replacement reaction. So then that's one way to do that. It's also important to note that a strong acid and a weak base creates a water and an acidic salt. And an acidic salt is anything, an acidic salt is basically when the salt is dissolved within water, the resulting solution will have an acidic pH. Um, so the solution will be slightly acidic. And that makes sense because if you have a strong acid and a weak base, well, since the acid is stronger than the base, they're going to react with each other, but then you're going to have some more acid because it's stronger. So it makes sense that we get acidic salts. And then the complete opposite is true. If you have a weak acid and a strong base, well, the base is stronger than the acid. So therefore, the resulting solution must be basic. And then anytime you see acidic salt or basic salt, that differs or that refers to how the thing is found within solution. So for example, a very good example of an acidic salt, just to give some example, is ammonium chloride. So I can show you what that looks like. So then for ammonium chloride, NH4Cl, the reason why ammonium chloride is considered to be a weak acid or an acidic salt is because it dissociates into NH4 plus and Cl minus. The Cl minus is not going to really do anything because the Cl minus is the conjugate base of HCl. And I know this because if HCl separates, I get H plus and Cl minus. However, because HCl is a strong acid, that means the opposite, the conjugate base, must always be a weak base. So that's always true. And you might notice, or you might have noticed, oh, I have, for example, acetic acid. I start off with a weak acid, but I always end off with a strong base. And that's always true. If you start off with a strong acid, you always get a weak conjugate base. Strong base, you get a weak conjugate acid. If you start off with a weak acid, you get a strong conjugate base. Weak base, you always get a strong conjugate acid. So anyways, going back to the acidic salt, the Cl minus is not going to really do anything. However, the NH4 plus will do something in that this NH4 plus can donate an H plus to the solution. So therefore, we get NH3, which is neutral, plus H plus. So then because this NH4 plus is giving up an H plus, we consider NH4 plus to be an acid. But if you might remember, it's coming from NH4Cl, which is a salt. So then we see that when the salts dissociate within water, it produces something that can give up an H plus, thus satisfying in definition for a Bronsted-Lowry acid. So that's why we call it an acidic salt, and that's essentially what we mean with acidic salts. And I guess for basic salts, anything that accepts an H plus, well, we can go back to this example of CH3COO negative. So if we have CH3COO negative, Well, I could easily have a salt such as sodium acetate, which is NaCH3COO. Yeah, NaCH3COO. And then when that does dissociate into water, I get Na plus, but that doesn't really do anything because that is a very weak acid, which I know because that's the conjugate acid of NaOH, which is a strong base. So then the Na is not going to really do anything. But the CH3CO negative will do something in that it can accept an H plus to produce acetic acid. So therefore, that's what we mean by basic salts because it's something that comes from a salt. So for example, sodium acetate, and then this acetate can then accept an H plus, thus satisfying our definition of a basic salt. Next thing we should talk about is the dilution equation. So then the general process is that once you obtain your stock solution, which is essentially a very concentrated solution and a volumetric flask, the reason why we use a volumetric flask is because it's more accurate for volume. Yeah, so we get those, and then using our dilution formula, you can figure out how many ml or L of the stock you'll need to obtain the diluted concentration of a desired volume. Then using a pipette, you add the required amount of stock into the volumetric flask, and then you use a squirt bottle, which is just water, to fill up the volumetric flask until the bottom meniscus hits the line on the flask. So the bottom meniscus refers to, this is like the very neck of the volumetric flask. And then you always have a line which represents the volume of the volumetric flask. So for example, if this was 100 milliliters, hitting this line represents 100 milliliters. And what the meniscus should look like is that it should look like this. You always use the bottom of the meniscus, not the top. And you might be wondering, well, what does this dilution equation look like? Well, it looks like this. So for example, we have the first concentration measured in molarity, M, times volume in either liters or milliliters, doesn't matter as long as your units are consistent, multiplied by the second concentration, multiplied by volume 2. So let's just say I start off with 20 molar of some compound, and I have sorry. So then so just to go over a quick example problem, let's just say I have 20 molar of a certain compound, and I do not know what kind of volume of that stock I will need in order to make that dilution. However, I do know that my desired concentration would be, let's just say 10 molar. And I wanted to have a concentration or a volume of 100 milliliters. So then the question becomes, what volume of my original stock do I need to add into my new volumetric flask? So I essentially set up the equation over here where I know the first concentration, I know the second concentration, and I know the volume of the second concentration that I want, but I do not know what volume of the original concentration I need to add. Well, we can essentially solve for V1 and figure that out. And it turns out that I will need 50 milliliters of this original stock plus 50 milliliters in order to reach our 100 of water, which makes sense because it's a half dilution. So then the math does check out. Um, and then along with the different classifications of reactions, there's also, which are the four main types, there's also, we can go into more specific types of chemical reactions that are less arbitrary than A's and B's. So then the very first type is the acid-base reaction, which we just covered, which involves the transfer of one or more protons between chemical species. There's also the oxidation reaction, oxidation reduction or redox reactions, which involves a transfer of electrons between two species, which we'll go into more, and the precipitation reactions, which are when two soluble salts in an aqueous solution combine to form one product that is insoluble. So for example, AgNO3 plus KCl goes into AgCl and KNO3. And when it comes to precipitation reactions, there's going to be a lot of double replacements. So the Ag swaps out with the case swaps out with K. So you get HCl, which turns out to be insoluble. So you get a solid. And then you get KNO3, which is aqueous, which is just a salt dissolved in water. So then when it comes to the solubility rules, you only need to memorize four for the AP exam. And those are sodium is always soluble in water. So sodium with some kind of compound will always be soluble. Potassium with another element will always be soluble. Ammonium with another compound or another element will always be soluble. And nitrate with another element will always be soluble. So these are the four solubility rules you should absolutely memorize. It's just four of them. Pretty simple. However, we do have a table for more complex relationships. You don't have to memorize these, I don't think. These four you have to memorize, but not the rest of these. You're going to have a table, most likely. So I would get some time, give some time to, be familiar with these. Table E and table F on your reference table. And yeah, that's pretty much it for solubility. Yeah, since we already covered a little bit solubility before. And then for the very last topic, let's talk about oxidation reduction or redox reactions, which, if we remember our basic definition, is essentially the transfer of electrons between two species. So when it comes to redox reactions, we always want to follow something called oxidation numbers. So oxidation numbers basically represent the amount of charge on a certain element within a chemical reaction. So for example, yeah, so we have the basic rules over here. Um, so for example, elements in their elemental form. So for example, if we have FeS, which is solid iron, iron is found within its natural state as solid because iron is a solid. The oxidation of that will be zero. Um, the oxidation number of a monatomic ion is the same as charge. So for example, if I have Na plus, the oxidation number that will be plus one. Oxygen has an oxidation number of -2, except when it forms peroxide, which has a oxidation number of -1. Hydrogen is -1 when it's bonded to a metal, but then +1 when it's bonded to a non-metal. Fluorine is always -1. And the other halogens have an oxidation number of -1 when they're negative. Um, there's also this rule over here. They also have positive oxidation numbers in oxyanions. You don't have to worry about the oxyanions. However, these two rules are very important. The first one being the sum of the oxidation numbers in a neutral compound is zero, while the sum of an oxidation number in a polyatomic ion is the charge of the ion. So just to go into an example, a very easy example is NaCl. So this is just an example of assigning oxidation numbers. Well, NaCl is neutral because I don't see any indication of charge, which means this has to be +1 because sodium is always +1 because that would be the ion that you have, while chlorine is -1. Sorry, 1 second. So that's that example over there, but then an example of a polyatomic ion, let's pick something from our solubility chart over here. NH4 plus, ammonium. So NH4 plus has an overall charge of +1. So let's just start over here. So hydrogen will always have a +1 charge because it's bonded to nitrogen, which is a non-metal. So I automatically know that the oxidation number of hydrogen in this ammonium will be +1. So then our total charge so far is 4 because I have 4 of these. So I have 4 +1 hydrogens. So then our next question is, well, what's the oxidation number of nitrogen? Well, is it +4 or -4 to kind of cancel out the 4 H pluses? No, because if you have a -4, it's going to make ammonium a neutral compound. So then it cannot be -4, but what about -3? Well, -3 plus 4 plus 1, because the hydrogens are plus 1, gives us plus 1, an overall charge of plus 1, which is exactly what we want because ammonium has an overall charge of plus 1. Um, yeah, so then that's that. So then those are some very basics of oxidation numbers. And another thing that we should talk about is actually balancing. Oh, sorry, before we go into that, we should talk about the difference between oxidation and reduction. Oxidation is essentially when an element is losing an electron. So if an element loses an electron, it is oxidized. When an element is reduced or undergoing a reduction reaction, it is something that gains an electron. You can use the mnemonic oil rig, which is oxidation is loss, reduction is gain. And another thing you should be familiar with is that anything that is oxidized is known as a reducing agent in that it causes something to be reduced so that it can be oxidized, while anything that is reduced is known as an oxidizing agent. The names are a little flipped, so be careful with that one. And for our very last thing, we should talk about how do we balance redox reactions. Well, before we go into the more complex redox reaction within acidic and basic solution, we should talk about balancing redox reactions in general. So over here, oh no, sorry, I did not get an example of a basic one. Let me see if I can get a basic one. Hmm. Sorry, let me try find a basic one. This is good. All right, so for this example over here, so this is a very basic redox reaction, and we could assign oxidation numbers. So when it comes to redox reaction, you always want to assign oxidation numbers. So the zinc will be 0 because it's an element, it's found within its elemental state. It's not an ion, so it's neutral. Cu, well, that's an ion. So then when it comes to our oxidation numbers, we always want to assign the charge of the ion as its oxidation number. So in this case, plus 2. Zinc, well, that's now an ion, so that becomes plus 2. And copper is 0. So then we see over here how the zinc loses electrons, so therefore we can say that this is oxidized. The zinc becomes oxidized, while the copper gains electrons because it turns from positive into 0, which means the only way you can do that is that if you gain negative electrons. So therefore, the copper was reduced. And when it comes to balancing this, we can do zinc goes into zinc 2 plus and 2 electrons because that's the amount of electrons that zinc lost. And we know this because it becomes plus 2. From 0 to plus 2, it had to lose 2 electrons. And you could double check this because the charge of the zinc plus is 2 plus, while the charge of the electrons that we have are 2 negative. So then 2 plus plus 2 negative is 0. While for the copper, well, we can break that off as copper 2 plus, and we know this has to be 2 negative electrons because copper is neutral, but then we see that we have the 2 plus charge and the 2 negative charge, add those together, you get 0. So then these will be our basic individual reactions happening within this oxidation reduction. So then what we can actually do is that we can flip the copper. And the reason why we want to flip the copper is because, or let me just write it out first. And the reason why we want to to flip it first is because we see in this actual reaction, the zinc neutral is on the reactant side while the copper positive, copper ion is on the reactant side. But then in this reaction over here, the copper ion is on the left-hand side. So we want to flip it and so that we can have it inside the correct orientation. The reason why it has to be flipped, well, that goes into second semester. That goes into electric potential. You don't have to worry about that now. And the neat thing with flipping now is that these electrons cancel out because we have two electrons on both the products and reactant side. So then those cancel out. And our final thing will be Zn plus Cu2 plus goes into Zn2 plus Cu. And I know that this is balanced because I balanced out my electrons. I have two on both sides, which is what I want. So then when it comes to redox reactions and balancing them out, you always want to balance out your electrons. That's like the biggest thing with redox reaction. And sometimes, some cases, this might be a 3 electrons, not for zinc, but then for a different compound, this might be 3 electrons. This could be 2 electrons. To fix that, you just multiply the top part by 2 and multiply the bottom part by 3. So that way you get 6 electrons because that's a common factor that's found between 3 and 2. Going into more complex examples, actually, this thing does a pretty good job at explaining what to do. So what I'll do is that I'll end the video now because my throat is kind of killing me right now, and I'll just send over this blog type thing because it goes step by step, which is really good. And this explains what to do for balancing reactions in both acidic and basic solutions. So yeah, so hopefully you found the video helpful, and I'll try to do some more practice problems tomorrow. See ya.